Okay, hello everyone. Today we're going to be talking about chapter 12 from the Fundamentals of Heat Transfer book. Uh, this book is the 7th edition by Bergman, Lavine, Incropera, and Dewitt. Okay, so these are what I've done is I've written out here kind of what I think the big concepts of chapter 12 are. So we're going to talk about concepts and then maybe run through an example problem to kind of help understand how this all fits together, right? Okay, so we're going to talk about the solid angle first. So the solid angle, this is where in the beginning of the book we have some sort of system, right? This is our system. It's just an arbitrary system, and in the book they draw this hemisphere around it. Sorry, so let me just draw a better hemisphere. So they draw this hemisphere around it, and they say that the solid angle you can think of as some area taken up in the field of view. So a good example I think of this is, let's say this is more of a 2D drawing. This is going to be your eye. So here's your pupil, your iris, and right now you're looking at the computer screen, right? So your eye essentially sees, to some degree, it sees this hemisphere in front of you, right? It doesn't see behind you, but it sees some sort of hemisphere in front of your body. And this computer screen takes up a certain area in your field of view, right? So what I would actually draw here is something like this, right? Because the computer screen's opaque. So you can see that the closer the computer screen is to your eye, the larger that area is going to be of the hemisphere, right? And the farther away it is, the smaller that area gets. So this is where they define, so first off, they define the differential solid angle as sine theta d phi, which is going to be important when we get into those triple integrals. And we have the finite solid angle, which we're going to use as an approximation regarding those triple integrals, where they say that it's the projected area divided by r squared. So this is where, the book calls it essentially a dimensionless area, where r is the distance from the eye to the computer screen or something like that, right? Now, this projected area, we'll talk about this projected area for a second. At the moment, the way I've drawn this, I guess I could call this drawing one. The eye is looking directly at the computer screen. And let me just draw the actual screen part in red. Okay, so in this case, the projected area is going to be length times width divided, and then the solid angle would be divided by distance squared. Now, you can see that what I want to do is draw a normal here, right? Okay, so the angle between the red line and the blue line here on this eye right here. So the angle between the blue and the red line is going to be 0 degrees. So the cosine of 0 is 1. So you're seeing the whole thing, right? Now, for a moment, let's rotate this computer screen. We'll rotate it like this. Okay. And now we still have our normal, but now this is our theta 1, right? You can see that we now have a theta. We do have some sort of distance between those two. We do have some sort of angle between the blue and the red line, right? And you can imagine that as we rotate this computer screen, right? And again, this red line is the actual screen. As we rotate it, let's say we rotate it 90 degrees, right? So now, keeping this blue line between the eye and the computer screen, draw a new normal. No, maybe this is normal too. We can see that this theta between the two right now is equal to 90 degrees. Okay. And what is cosine of 90? It's 0, right? So this makes sense, right? So sit in front of your computer screen, rotate the computer screen 90 degrees. Can you see the screen anymore? No, right? So this is where for the finite solid angle for the projected area, they add a cosine theta here. And the cosine theta is that theta between the normal and the ray of irradiation. And you can see that when you're sitting directly in front of it, the computer screen, so the theta would be 0, you see the whole computer screen. But as you rotate the computer screen, you see less and less of it, right? So hope that example helps. That's a solid angle, right? The projected area for a sphere is a circle, right? So I guess it's the 2D area, right? Like you only see the circle, right? So projected area for a sphere is equal to just pi r squared, where little r is the radius and large R is the distance. This notation, large R used by the book, right? Okay, so that's a solid angle. So again, it's just simply the amount of, it's the area that some object takes up of this hemisphere, right? And this eye that we drew here, it can be anything. It could be a detector, a rocket ship, a thermocouple, I don't know, whatever you want it to be. This eye would represent your control volume, your system, right? So maybe I would do that in green because it's always important to draw your system, right? So that's your system. And then your system is receiving some irradiation. In this case, your eye is receiving electromagnetic radiation from the computer screen. Okay. All right, so we got solid angle. Irradiation, right? So irradiation is this G term that they talk about in the book. So this is always incident, right? Okay, so for example, you have your absorber plate for your project, right? Like you have some sort of G sun hitting it, right? So this is always something that's incident on the surface. Okay, and then they define G as 0 to infinity, 0 to 2 pi, 0 to pi halves I incident lambda theta phi cosine theta sine theta d theta d phi d lambda. Okay, now we're going to talk about these triple integral definitions a little bit later. They're really important, and if you can get a really good handle on them, you will be sitting pretty well for your final exam. Okay, so irradiation is always incident, right? Now, whether that's light from the computer screen, electromagnetic radiation from the sun hitting your absorber plate, you could have some sort of furnace emitting some radiation that's incident on the detector, right? So whatever incident, that is irradiation. And that irradiation, for example, for the example of your absorber plate, the irradiation incident on the plate is also connected. It's not equal to, but it's connected to the whatever the sun is emitting, its emissive power, right? Okay, so again, irradiation incident on the surface. Emissive power is just anything with a temperature greater than 0 K has some sort of emissive power, right? So your body has some emissive power. The desk you're sitting at is emitting some radiation because it's at some sort of temperature, right? So anything that's not at 0 K has some sort of emissive power, okay? And this is likewise almost the exact same thing. They're the definition for emissive power. The only thing that changes is the subscript. Instead of the intensity incident, it's the intensity emitted. Lambda theta phi cosine theta sine theta d phi d lambda. Okay, anything, so we have irradiation, anything incident on the surface, emissive power, anything being emitted, so anything with a temperature has some sort of emissive power. Now we go to radiosity. Likewise, only the subscripts change. 0 to pi halves. This is now radiosity is emitted plus reflected. Lambda theta phi, whoops, cosine theta sine theta d phi d lambda. Right, so radiosity is just a combination of, you know, if you had your absorber plate right here, right? If you have your absorber plate, you have some G sun hitting here. You have some reflected G sun, and you also have some emissivity. Okay. So the radiosity is just a combination of these two terms. Intensity. Intensity is a conserved value. So let me emphasize that. Intensity is conserved. So the spectral directional intensity, this has units of watts per meters squared direction. I'm just put direction as a unit here. I don't, whatever direction you want. And meters for lambda. Okay, steradians. So steradians is that dimensionless area unit, right? So for a diffuse surface, this then becomes watts per meter squared, meters for lambda and wavelength, steradians, right? So maybe what I would do is erase this. I could put lambda here, right? And so if we integrate, then the total intensity, the units are watts per meter squared steradians. So here you can see that in order to get a flux, right, these are the units of our G, J, E, which all include an I term in the integral. In order to get we're going to have to multiply by a steradian. So essentially multiply by a solid angle. Okay. So G is incident, E is emitting from the surface, J is just simply whatever is reflected and emitted combined. Okay. Let's talk a little bit about surface properties. So absorptivity, that's the alpha term. Okay, so this absorptivity is just what's absorbed into the surface, right? So your absorber plate, let's say you're interested in the temperature of the absorber plate, right? So you choose the absorber plate as your system, and you have some alpha G. Okay, G sun, right? So the G sun for the Earth is equal to 1387 watts per meter squared. Okay, now if alpha is 0.8, it's just 80% of that, right? So that's what alpha is saying, is that it absorbs 80% of whatever's incident, 20% of whatever's incident. Okay. Likewise, emissivity is just a percent of how close it is to a black body, right? So if it's 0.2, then it's 20% like a black body. If it's 0.5, it's 50% like a black body. So I could comparison to a black body, right? So if it's 100% where epsilon is equal to 1, then it's 100% a black body, which is good because we have several equations of black bodies, and then all we need to do to relate those equations to real surfaces is know an emissivity value. Okay, we have transmissivity. That's this tau term. That's just how much transmissivity. That's how much passes through, right? So like this was the absorber plate. In your project for your solar water heater, you might have this absorber plate here. And then you have your cover plate, your convection cover plate, right? And then what's assumed is, okay, yeah, so the transmissivity is simply how much passes through, right? So for example, in your project, it would often be assumed that this cover plate is fully transparent. In other words, all of it is transmitted through the cover plate to the absorber plate, right? Now, if your transmissivity was 0.8, then that means that there is either some reflectivity or absorptivity or both in the cover plate itself, which for a real surface, that would definitely have some effect, right? So transmissivity is simply how much passes through to the other side of the surface. Okay, and then we had reflectivity. Reflectivity, again, that's just whatever's reflected, and that's rho, that's just whatever's reflected off your cover plate, right? So there might be some rho here, maybe. That really is dependent on the problem setup. Okay, so Kirchhoff's law, you should definitely know Kirchhoff's law for the test, right? So Kirchhoff's law is this. It says that the spectral directional absorptivity is equal to the spectral directional emissivity. Okay, I want to underline this because this is incredibly important. Many people think that Kirchhoff's law is alpha equals epsilon. That is not Kirchhoff's law. That is an application of Kirchhoff's law to a specific case. So I'm going to write not Kirchhoff's law here, although this equation may be true for certain cases. Let's talk about those cases. Okay, so we know that gray means, gray is not a function of wavelength. So let's apply Kirchhoff's law to a gray surface. That means if it's not a function of lambda, we just erase the lambdas. Okay, so then we say the directional absorptivity is equal to the directional emissivity, right? And then we say for diffuse, it is not a function of theta, right? So continuing, we just erase the thetas and we say alpha is equal to epsilon. This is true for gray diffuse surfaces only. Okay, so in your exams, if it's not gray and diffuse, do not say alpha is equal to epsilon. Okay. Big hint for you is if they give you this graph where they say alpha lambda as a function of lambda. This is a big hint that it's not gray. It is diffuse, unless they were to provide you a graph of how it changes with direction too, which is often not the case, at least for ME 340. This would tell you it's not gray. So you can say alpha theta is equal to epsilon theta, but you cannot say that alpha is equal to epsilon. Okay. Now, often a companion to Kirchhoff's law is just this summation where it has alpha plus rho plus transmissivity is equal to 1, right? So transmissivity for opaque surfaces is equal to 0, which makes sense if it's opaque, right? So then for opaque surfaces, you have alpha plus rho is equal to 1. So let's say they give you rho, lambda, and some graph, right? And you're trying to figure out what the absorptivity of this surface is. The absorptivity of this surface is going to be 1 minus rho, right? So if this is 0.2, this is 0.8, you can use this summation rule and you can draw out your absorptivity as a function of lambda, right? Where this might be lambda c, this is lambda c, right? It's just the inverse of that. Okay, now let's say you wanted to know okay, let's say you wanted to know what is the emissivity values. Okay, so this is where you use Kirchhoff's law for a diffuse surface. And oh, I may have said something slightly wrong up here relating to this. So be aware. I believe I said that if you get a graph like this, then you can say the directional absorptivity is equal to the directional emissivity for just a gray surface. I don't remember if I said diffuse or not, but that would be only for a gray surface, right? In this case, many times down here, coming back to this, most of the time in ME 340, we're given a diffuse surface that is not necessarily gray. So in this case, let's apply Kirchhoff's law for a diffuse surface. Okay, so let's remember that's alpha lambda theta is equal to epsilon lambda theta. If it's diffuse, erase the thetas. Alpha lambda is equal to epsilon lambda. And you already have a graph for alpha lambda, and it's going to be the exact same graph for epsilon lambda. The spectral absorptivity equaling the spectral emissivity. Okay, so in an exam, they might tell you you have an opaque surface and you have a graph for reflectivity. Can you relate reflectivity to absorptivity and emissivity for an opaque diffuse surface? If not, I would study this a little bit more. This is really, really important because this shows mastery of a lot of different parts of chapter 12, right? Because if you remember, you have your absorber plate here, right? So this is our control volume. You have some alpha G sun coming in, right? And this is not complete, but because I'm just focusing on radiation right now. And you might have some emission, you will have emissive power coming out, right? Okay, so given a graph of reflectivity in your project, relate reflectivity to absorptivity for an opaque surface using this summation rule right here. And then using Kirchhoff's law for a diffuse surface, relate absorptivity to emissivity, right? Because this emissive power value is going to have an emissivity value in it, right? Okay, so before I start getting into examples and stuff, one more concept I want to cover, and that's the band emission, right? Using fractal functions. So that's this like F, and then you'd have like 0 to 3 micrometers or something, right? What it is let's say you have a graph. This is lambda, and this is your intensity emitted, right? Now, if you have this graph, let me draw that. Or sorry, I'm going to say emissive power, right? Let's say you have some graph like this. The fractal function, so this F value for 0 to 3 would be defined as the emissive power from 0 to 3 over the emissive power from 0 to infinity. That's essentially what it is. Okay. So if here's 3 micrometers, what we're doing is we're taking the blue shaded area and we're going to divide that by the red shaded area. So conceptually, what is the largest value F could ever be, right? The largest value it could ever be is red divided by red, which is equal to 1. Okay, so the fractal function with the band emission fractal function stuff, that is simply a fraction representing how much of the power is emitted in that band. Okay, so this is really important when we're for non-gray surfaces when we're calculating surface properties such as emissivity and emissivity and absorptivity. Okay, so I think those are the major concepts, right? So again, we have solid angle. It's just the amount of, it's just an area taken up over the hemisphere that your eye would see. G is an incident. So radiation is a broad term, right? So in radiation, you have subsets. So irradiation is a subset of radiation. Emissive power is a subset of radiation. Radiosity is a subset of radiation, right? Irradiation is what is incident. It's what's coming in. Emissive power is what's coming out. What's emitted by, sorry, it's not what's coming out, but it's emitted by the surface. Radiosity is a combination between emissive power and reflectivity, right? So these 3 cases right here, they're just subsets of the broader term radiation. And these are just denoting what's coming in and what's leaving, essentially. Intensity, conserved value, right? So it's maybe I didn't finish explaining that, and I apologize. Intensity is a conserved value. So the intensity of the sun on Mercury, right? So versus Pluto, and for a moment, let's assume that Pluto and Mercury are the same size. I don't actually know how close they are to the same size, but the intensity emitted here to Mercury is the same as the intensity emitted to Pluto. And Earth and Mars and Jupiter, Saturn, right? All of them, they're all the same intensity. However, it's obvious that Mercury is much hotter than Pluto. And why is that? That's because of this solid angle term, right? If you remember, we had we said that E for a black body is equal to pi IB, and then we know the emissive power of a black body is sigma Ts to the fourth, and then we can solve for I divide by pi. Okay, so you see in here, the intensity is the same no matter what. I mean, this is just a function of temperature, right? So it doesn't matter where you are, the intensity of the sun is the same. But if you remember a couple of the example problems, your G term essentially is going to have an I times delta omega, right? And what's delta omega? It's projected, let me write that down here. I sun, and then you have projected area of the sun divided by distance squared. Projected area of the sun doesn't change. It's a circle, a disk, right? Pi r squared. IS doesn't change, but r squared changes dramatically between Mercury and Pluto. And so that's why the G term, the incident irradiation, is much different between Mercury and Pluto, but the intensity is the same. Okay, so intensity is a conserved value, which is why it's used in all three of the G, J, and E triple integral definitions. Our surface properties, we have absorptivity, what's absorbed into the surface, emissivity, what the surface emits, transmissivity, is the surface opaque or not, and reflectivity, how much of it's reflected. Kirchhoff's law was the spectral directional absorptivity is equal to the spectral directional emissivity. And then we can use cases of gray and or diffuse in order to simplify that and apply it to our problem. Band emission is just the amount of power emitted in that wavelength divided by the total power emitted by the body, right? Okay, so those are kind of the big concepts of chapter 12. And now I thought it might be helpful to run through an example problem, right? So in this example problem, we could have the sun, right? And we can have a rocket ship approaching Mars, right? So this isn't to scale because this would be a fairly large rocket, right? But let's say this is the rocket approaching Mars, since that's a big topic in space right now. And we want to know what we want to know how much is this surface absorbing from the sun, right? Because we don't want it to boil the fuel inside. So the colder that we can keep this outside, the colder we can keep our cryogenic fuels, and the less we're boiling off into space, right? So this is what we would do is choose a system, right? So what are we interested in? We're interested in the temperature of the rocket, right? Okay, so let's choose a system, right? So the rocket is my system. Okay, what interactions do we have? Well, space is a vacuum, so there's no convection and there's no conduction happening, at least what we're considering here. There's no conduction happening across the boundary. Obviously, there's some conduction on the inside. There's temperature gradients between walls and insulation and tanks and stuff, but let's just look at the surface temperature of the rocket, right? So we will have some G sun, alpha G sun coming in, and then so no conduction, no convection. What are our three types of radiation, right? We have irradiation, we have emissive power, and we have radiosity. I'm going to choose not to use radiosity here, although you could. I'm going to just say we then also have some emissive power coming out, and we want to know the steady state temperature of the rocket wall when it's a distance Mars away from the sun. Okay, the other way to set this up, if you wanted to use radiosity, right? Maybe I do it in red instead, right? So radiosity would be something you would have J coming out, and you would just have G coming in. Okay, you wouldn't, because J is using reflectivity, right? And remember what reflectivity is. It's 1 minus alpha, right? And in green, I chose to use alpha instead of reflectivity. So you can do green or red. I prefer green personally. I really don't use the specific radiosity term very often. Okay. All right. So now we say alpha G sun, and let's say that they give you this graph, right? So we have rho lambda lambda. Let's say we have two cases, right? So this would be case 1, and this would be case 2. This would be a very good, similar Dr. Jones question to something I've seen in the past, right? So this case 1, let's say we don't paint the rocket, right? Or let's say we just paint it with something normal, I don't know. So let's say that the reflectivity here is going to be 0.5. But then let's say we use a special case of paint, right? Where it's 3 micrometers, okay? So the the reflectivity is going to be 0.9 until 3 micrometers. And then let's have it drop to 0.2 micrometers, or sorry, 0.2 at 3 micrometers. So then the question becomes, should we paint the rocket, right? Okay, so first off, let's draw out our energy balance, okay? So we have alpha G sun minus emissive power of the rocket. And then technically both of those are, okay, multiplied by A. This is minus E. A equals 0. Okay, technically this A is kind of like the projected area, right? So, well, maybe I'll just simplify it. So this A would be like the projected area of a cylinder, right? So looking at the cylinder from the side, the projected area would be a rectangle. And then this A on the emissive power term would be the surface area of a cylinder, right? So 2 pi r times L. Depending on how exact you want your solution to be, this could be important or not. So what I'm going to do for just to simplify the problem is cancel out the areas. To be more exact, you would leave the areas in there. Okay, so we have alpha G sun minus emissive power of the rocket is equal to 0. Okay, so now we're still looking for a way to get some of these terms, right? So first one I would start with is G sun. You could start with any of the others. I would start with G sun, right? And then what is it? Okay, so I know a definition for G. That's 0 to infinity, 0 to 2 pi, 0 to pi halves, I incident, lambda theta phi cosine theta sine theta d phi d, oh, sorry, wrong d omega, because it should be d lambda. Okay, so whenever you have one of these triple integrals and you're using the method of chapter 12, you want to ask yourself, is the solid angle much less than 1? The finite solid angle. So what's the finite solid angle? Remember, that's the projected area divided by r squared. The projected area for a sphere is pi r squared over distance squared. Okay, and remember, what's our system? Our system is the rocket. So if we're on the rocket looking at the sun, it takes up this solid angle, right? So this is going to equal, I had the values here. Where did I set them? Okay, got them. This is going to be pi, and then the diameter, at least I have the diameter of the sun, 1.3927 times 10 to the 9th. That's going to be divided by 2 to make a radius, make that squared. And then the distance is going to be 222.78 times 10 to the 9th squared. Okay, now if you were to do this, you would find that it is indeed much less than 1. So this is the difference between chapter 12 and chapter 13. Some people have been asking, like, when would I use chapter 12 when I can just always use view factors? So you can always use view factors. And if you feel more comfortable with using view factors for chapter 13, go ahead and use view factors. However, this one is really nice. Chapter 12 is nice once you get the hang of it, because oftentimes you'll have funky shapes and you won't have view factors. So if you look in chapter 13, in table 13.1 for the 8th edition, I believe, 13.2 for the 7th edition, I believe. If there is a view factor from a rectangle to a disk, go ahead and use it. If there's not, then you want the solid angle to be much less than 1 so that you can use chapter 12, because you don't have to do any big area integrals in order to find a view factor by hand. Okay, so find out this is much less than 1. So let's use chapter 12. Chapter 12, we're going to use this definition of irradiation. Okay, so then we ask ourselves in red, how can we simplify this integral? Okay, so I'm going to recognize that this is the definition of the differential solid angle. So G is equal to 0 to infinity, right? Finite, and then we turn this into an area integral. D omega d lambda. And then we ask ourselves, is I, intensity, and cosine theta, are those functions of the solid angle? Do they change over the solid angle? The answer, if this approximation right here, delta omega much less than 1, if this is true, then we approximate them as constants, I and cosine theta, as constants with regards to d omega. Just to give you an idea of why, if we take your I, right, and we have the computer screen, and it's all the way over here, right? And I ask you, oh, whoops. Now, obviously, there's some limitations to my drawing. I apologize for that. If I drew it more carefully, maybe it wouldn't happen. But essentially, I would ask you, there's two lines coming out of your, two lines representing the irradiation from the computer screen on each ends coming into your eye. Conceptually or qualitatively, could you tell me the difference between the two lines? And the answer is no, right? Like, they essentially look like they're the same. So mathematically, is there a difference? Yes. But we say that it's negligible because it's so small. Okay, so this is the chapter 12 way, right? If delta omega is much less than 1, we can simplify this integral. And we can say g is equal to this, pull these out, and that's no longer a function of omega, delta omega d lambda. Okay, now we need to solve this bracketed integral. If I asked you if I had area of a circle here, dA, and I asked you to solve that integral, conceptually, what would you say? Well, the indefinite integral of dA would be a plus c. We could set c equal to 0. So it'd just be a. And then I'd say area of a circle. So a would be equal to area of a circle. Right? And we have a definition for that. That's pi r squared. So you could tell me this, right? So likewise, we're going to say the same thing. This integral, this bracketed integral, is finite solid angle. That is the result, right? So we're going to say delta omega d omega is equal to delta omega, right? And what's delta omega? That's the area times the cosine theta, because that's the definition of projected area, divided by r squared, distance squared. Okay, so we can pull out the finite solid angle. That's not a function of lambda. Is cosine theta a function of lambda? Again, the answer is no, unless you had some problem where the red light from the sun was hitting the rocket at a different angle than the yellow or the green or the blue light. But it's all just, well, and I don't really know any cases where that happens, unless you had some sort of glass prism separating out the wavelengths. So you say it's pretty safe to say it's almost always cosine theta is a constant with regards to lambda. Okay, and then we have the incident intensity d lambda. Okay. All right, now we're looking at the irradiation from the sun over all wavelengths. So we just need the total intensity, right? So this red box right here, that is the definition of the total intensity. So you say G is equal to delta omega cosine theta. And then I of the sun, the total incident intensity from the sun. That's the definition. So what is that? So this is where you have to go back, and what you want to do now is relate it to something like emissive power. So the Stefan-Boltzmann law says that emissive power of a black body is equal to sigma Ts to the fourth. Okay, so then you ask yourself, is the sun a black body? Yes, it's a black body. Okay, so we can use this law. If it wasn't, emissive power for a real surface, for a real diffuse surface anyways, is epsilon sigma Ts to the fourth. Okay, but for a black body, emissivity is equal to 1. Okay. Now, what you'd want to do is there's also another equation in the book where we say E is equal to, the emissive power is equal to pi I for a diffuse surface. So we say sigma Ts to the fourth is equal to pi I. This would be total intensity. So total intensity of the sun is equal to sigma Ts to the fourth over pi. Okay, so now we plug that in. G is equal to delta omega cosine theta sigma Ts to the fourth over pi. Okay, now we assume that the ray of radiation hitting the rocket, because it's so far away, that essentially it's all normal to the surface, right? And if it's normal to the surface, remember that this cosine theta, theta is equal to 0. Because it's the line, it's the angle between the red and the blue line that I've just drawn, and that's equal to 0. Because delta omega is so small, we say that it's non-varying across the rocket, right? So cosine theta, cosine 0 is 1. So G is now equal to delta omega sigma T S to the 4th over pi. Okay, now the delta omega, we do the projected area, right? And that's the projected area of the sun, because remember what our system it is. Our system is the rocket, right? So what does the rocket see? The rocket sees the sun, so the projected areas of the sun. Okay, so this is the pi times 1.3927. That value squared divided by 222.78 times 10 to the 9th squared. Okay. Pi r squared, and then we have sigma. Temperature of the sun is 5800 K. So things like temperature of the sun, distance from the sun to Mars, and diameter of the sun, those are either lookup values or they are givens. Pi. Okay, so this is going to come out to some value, right? This is G sun. I don't have that value with me. I won't grab my calculator right now, but this comes out to some value, and that's just plug it into your calculator, right? Okay, so now we have two values left. We have alpha and emissivity, right? So alpha. So this is where you have to realize, first off, is the surface gray or not? So let's go back to the problem definition. Oh. So in this problem definition, they give us rows, right? So how can we find alpha using rho? So that is to remember that alpha plus rho plus transmissivity is equal to 1. So if the rocket is opaque, transmissivity goes to 0. Alpha is equal to 1 minus rho, right? So then alpha lambda, we can now make a graph of alpha lambda. For the first case would be 0.5. And then for case 2, right, alpha, I believe this one was, the reflectivity was 0.9. So that means alpha is 0.1 here, and then it was 0.9 after, right? Or it would be 0.8. Yeah, okay. So it starts off small and ends up bigger, right? Where I believe this one was 3 micrometers. All right, so now how do we find total alpha? So in order to find total alpha, we can use the fractal functions. We can say alpha, right? Alpha is equal to alpha lambda 1, and then we're going to use the fractal functions f. And actually, I apologize. We don't have to do that for case 1 because it's not changing with regards to lambda. Remember, this was some problem I just came up with as an example, right? So we don't have to do that for case 1. We know what alpha is, right? Because if we were to use the same approach that we're going to use for case 2, this one would be alpha lambda 1 f 0 to infinity, right? And if you remember, fractal functions tell us the amount, the fraction of power emitted in a band, right, for a given body. So it can never be greater than 1. But if you're integrating from 0 to infinity, that is the case where it's 1. So this becomes alpha is equal to alpha lambda 1, which is equal to 0.5. Okay. Now, for the second part, we would say alpha is equal to alpha lambda 1, and then we want to multiply by the fraction of power emitted, sorry, the fraction of power absorbed from 0 to 3, right? And then we'll also add in the fraction of power absorbed from 3 to infinity. Okay, so we have values for alpha lambda 1, alpha lambda 2. So let's say this one is 0.1. And then we want to calculate the fractal function. So the fractal function is going to be lambda t. And let me f lambda t, and then it spits out a column in the second value for table 12.2 in chapter 12. Okay, so first off, what we would do is we would say f times 3, and I'm going to leave this blank, minus f 0 blank, right? But you'll notice in the table that if you're starting at 0, right, this is always going to be 0. Okay, so now we have F3 times some temperature. So now you have to ask yourself, like, do you use the temperature of the rocket, or what temperature to use? Because this is alpha this is alpha as related to G sun, we're going to use temperature of the sun. Okay, so whenever you're finding alpha and you use the temperature of whatever is emitting and becoming incident on your system of interest, right? So this one would be 5,800. Okay, and that's going to give you some value, right? That's just a lookup value now in table 12.2 in the second column, right? So I could, so I'll just leave that. Okay, now for the second part, you say, well, how do I integrate from 3 to infinity? Well, remember what we know, f0 to 3 plus f3 to infinity has to be equal to 1, right? When we integrate over all wavelengths, we're saying the emitted power over all wavelengths divided by the emitted power over all wavelengths, right? So that can never be larger. I mean, it always has to be 1, right? So what you can say, you can actually solve, you can say f3 to infinity is equal to 1 minus f0 to 3. Okay, so we've already found f0 to 3. That was this value here. And so now we have alpha is equal to 0.1 times f0 to 3, which we found. Again, remember that's this. You do 3 times 5,800, so that's going to be a little less than 15,000. You might have to do some interpolation. Look it up in the table. Plus 0.8, I believe I said it was, times 1 minus f0 to 3. So you can do that now. Okay, so now we have values for alpha, we have value for G, and now we need to find a value for E. Okay, so again, if you remember, let me come back over here maybe. Emissive power of a black body is equal to sigma Ts to the fourth. That's the Stefan-Boltzmann law, right? So emissive power of a real surface is just epsilon sigma Ts to the fourth. This is going to be whatever temperature is getting emitted, right? So this is the rocket temperature, which is great because now we know in alpha, we know a G sun minus epsilon sigma Ts to the fourth is equal to 0. We know sigma, we do not know epsilon, and then just we're solving for Ts to the fourth, right? Okay, so how do you find epsilon? Okay, so if we go back to the concept list, right? Like if I were to come up here and say, all right, what concept here helps me find epsilon? I would realize that Kirchhoff's law will help me, right? Kirchhoff's law. What was Kirchhoff's law? Okay, Kirchhoff's law was this: alpha lambda theta is equal to epsilon lambda theta. All right. It's a diffuse surface, so we say alpha lambda is equal to epsilon lambda. So now you can do the same thing, right? So you come over to your chart, right? And that was at 3 micrometers. This is 0.1. This is 0.8, and this is epsilon lambda. So following the same process, we want to find total epsilon. Okay, total epsilon. In this case, we would say epsilon lambda 1 times f 0 to 3 plus epsilon lambda 2 f 3 to infinity. So we know epsilon lambda 1, epsilon lambda 2. Now remember, this is now emissivity. This is not absorptivity. So absorptivity, we do whatever temperature is coming in. Emissivity, we do whatever temperature would be emitting, right? So coming in would be the sun in this case. Coming out would be the rocket in this case. And now here you might ask yourself, oh, but in order to calculate fractal function, I need to know the temperature of the rocket, but I'm solving for the temperature of the rocket. So in this case, you would have to do some sort of numerical solution until it converges. So pick a temperature and guess, right? I don't know, choose 300K, you know, just guess whatever. Make a reasonable guess. I wouldn't guess somewhere close to the temperature of the sun, but make some sort of guess, right? Because now you calculate an epsilon, right? Because that's 0.1 times f 3 times 300 plus epsilon lambda 2, which was 0.8, right? F, and then it would be 1 minus that, right? 1 minus f 3 times 300, right? And you'll notice, like if you look in your 3 times 300 is 900, right? So you go to your table 12.2, look at the first column, 900. That's essentially 0, right? Even if you raise it to 500K, you're still in the thousandths of the fraction, right? So this one would you can make a pretty good guess in the beginning and get pretty close with the first guess, I think, just because the total fraction is going to be, there's not a whole lot emitted in that first little band. It doesn't change a lot. However, in order to make a proper solution, you would have to guess a temperature here, 300K, go through, and then let's say you get the temperature of the rocket is actually 500K. Because now, once you solve this total epsilon value, we have total alpha, total G, we have epsilon and sigma. It's pretty trivial to solve for TS. And you could get the 500K, then you'd run back through, put 500K in for the fractal functions, and the solution would eventually converge. Okay, so, and then remember here, just to simplify the problem, I just canceled out the areas. That's important to note that that was a pretty big simplification. To make it a little bit more exact, you would maybe add a 2 here, right? Because it'd be 2 times the area. And then if you really wanted to be exact, you could actually plug in the areas, like if you were given that. Okay, so we've run through a problem with chapter 12. So let's think just for a moment. I know this video is a little long and I apologize, but there's a lot of important concepts here. So solid angle, right? So I keep repeating these things, but there's so many things in this chapter and also chapter 13, but they will be immeasurably important for you on your exams. Okay, so solid angle, right? So we have the d omega and we have delta omega, right? D omega we use simplifying the triple integrals, and then getting the delta omega, which is just the definition of the projected area divided by the distance squared. Right, you can see, like, again, like computer screen, as you move your computer screen farther and farther away from you, the actual area of the screen hasn't changed, but the area that your eye sees in regards to the total hemisphere does change, right? So there's things like that, and that was demonstrated in the difference between the sun and Mercury and the sun and Pluto, and how that affects the incident irradiation. So remember, irradiation is always incident on the surface, it's always hitting the surface. Emissive power, that's anything with a temperature greater than 0 K, is emitting some sort of power. Radiosity was just a combination of the emissive power as well as the reflected power. Intensity is that conserved value, watts per meter squared, to radian, lambda, and that it's the same whether it's on Mercury or Pluto, but it's the irradiation that changes because the solid angle changes. Okay, the surface properties, absorptivity, so absorptivity, transmissivity plus reflectivity is equal to 1. Remember Kirchhoff's law, which can relate absorptivity and emissivity. And then the band emission, which is just simply the fraction of emitted power divided. So the emitted power of a band divided by the total emissive power of the body, right? And that was important because we use that to solve for certain surface properties, right? So we use it to solve for total alpha. We use it to solve for total emissivity. But we use different temperatures, remember. The temperature for alpha was whatever was the temperature of the sun in this case. Whereas the temperature we use for the fractal function calculating the total emissivity was the temperature of the surface, and in this case we had to make a guess. Drew out an energy balance, made some simplifications, solved for each of the terms, came here. Again, in this case, you'd have to converge. You'd have to run through 1 or 2 iterations to get the solution to converge. But there's a lot going on, but if you break it down, it's really not bad, right? So pick a system, draw the interactions with the system, right? Then you'd start going through your terms. All right, how do I find alpha? How do I find G? How do I find E? Alpha, total alpha, we used Kirchhoff's law to relate reflectivity to alpha. And then we used the band emission to find the total alpha using the temperature of the sun. Then we said, how do we find G sun? Okay, we use the definition of G. Okay, so just plug in definitions. And then this was the chapter 12 way. Delta omega is much less than 1. If not, you would have to use chapter 13. Then emission, you can also run through the definition of emissive power with the triple integral for a diffuse surface if you would like. What you get is the same result that we got here using the Stefan-Boltzmann law, right? Where we said emissive power of a black body sigma t to the 4th. We can relate that to epsilon sigma t to the 4th. And then again, because this would be receiving radiation on one side, but emitting at all directions, I just multiplied by a 2 here just to make it a little bit more exact. Okay, and then to calculate epsilon, we used Kirchhoff's law, but this time using the temperature of the rocket and making an initial guess. Okay, so it's the same process you've been doing, right? So system, interactions, energy balance, and then just run through definitions. And I'm fairly confident that if you guys run through this a little bit, you'll be able to rock it on the exam. I apologize, the video is a little long. Again, if you have any comments, ways to make it better, break it up more, things to add, let me know. Okay, and I hope you have a great day and good luck on your exam.